Hey folks, thanks for joining me here on YouTube. Since I'm out today, I'm going to give you this lesson online so you can watch it at your own pace, take notes, and get ready to practice some things. The focus of today is series and parallel circuits through the lens of what are known as Kirchhoff's rules. These are rules that he came up with to summarize what happens in an electric circuit based on experimental data and also physical, like scientific principles. As you can already tell, this video is kind of roughly made, so I apologize for any lags in coherence. So we'll start right off with the junction rule. So the junction rule is generally the easier one to understand. It focuses on current, and the basis of this rule is conservation of charge. So when you hook up a circuit for the first time, the number of electrons in that circuit that can move is constant as long as the circuit is running. So you're not losing or gaining any electrons from the circuit. The rule is worded: the total charge entering any point in a circuit must equal the total charge leaving that same point. So for a series circuit, you can pick any point you want. So I'm going to pick this point since it's like the middle of the circuit across from the battery. Technically, now I've identified a junction. A junction is where things like branch off or come together. Neither of those things happen here, but that doesn't happen at all in a series circuit. So the rule says the number of electrons entering that point has to equal the number of electrons leaving that point. And so what that means for this circuit is, well, this current, the total charge is represented by the current that's moving here. So the total charge that moves through this resistor is the current through it. So I'm going to give that the designation of I1. So the current that leaves this resistor gets to this point, and then the current that goes through this point or leaves that point then goes through the second resistor. So I'm going to label this I2. And so the current that leaves this one is I1. The current that enters this bottom one is I2. And so according to the junction rule, these two currents have to be the same. That I1 is the current that enters that point, and I2 is the current that leaves that point. And so I get this really quick idea about series circuits, that I can pick any point that I want, and the current going into it will always equal the current leaving it. So I can make kind of like a sub-rule, and that is that the same current is everywhere in a series circuit. Because if I put my junction there, then the current leaving the battery has to also be the current going through R1. If I put my junction here, the current leaving R2 has to be equal to the current going in the battery. So everywhere is a one path street, and so the current is the same everywhere for a series circuit. The other application of that is for a parallel circuit where everything's on its own path. You'll get used to building and working with these if you are not already used to it. For the rule to kind of show you what a parallel circuit is all about, I have to pick this point or this point as my junction. So I'm going to pick this point up here. And so I'm going to do the same thing. I'm going to draw some arrows. So that represents the current that goes into that junction, and then these arrows represent the current that comes out of it, because this is an actual intersection. So the current here hits this point, and then these are electrons. So electrons have to either go to the left through R3 or to the right through R4. So let me label these. This top line, I'm going to label it IT because it's the total current. If I follow this, now that I know about junctions, there are no junctions all the way through the first part of this circuit. So the current that leaves the battery doesn't change at all until you get to this junction here. Then I have this path on the left. I'm going to label it I3 because it's all the current that's going to go through I3. I'll label this one I4, and so that's the current that's going to go through I4. So the junction rule says that the total current entering this junction, which I have labeled as IT, is equal to I3 plus I4. So I can build this equation because I know that all of this current goes into the junction, and then some of it goes to the left, and the rest of it has to go to the right. There's no third option, and so these two currents have to add together. So in a parallel circuit, I get a different rule. The individual currents add together to the total. And so I get that rule that's different for series and parallel. So current behaves differently in series as it does in parallel. In a series circuit, you get the same current everywhere. In a parallel circuit, the individual branches currents add together to make the total, because you have all the electrons come through this first part, and then the current divides in pieces, and then it rejoins itself to go back to the battery. So that's Kirchhoff's junction rule for current. Next up, we have Kirchhoff's loop rule. This one's a little bit harder to explain because we haven't talked a ton about all of the things leading up to voltage, but it's still pretty simple. The loop rule is an application of conservation of energy, and it says for any complete loop in a circuit, the voltage across the battery must equal the voltage across the remainder of the loop. So that if you learn this later in life, like next year or in college, the wording is very different. And so I've kind of cut some corners because we're cutting some corners with electricity. So the voltage across the battery must equal the voltage across the remainder of the loop. And so I have labeled some circuits here. I'm now going to label the battery voltage as well as VT. Okay, so this is a series circuit. It has two resistors in series. So this is like pretty easy for any complete loop. So if I start at the battery, the loop would go through R5, R6, and it would come back to the battery. So that's a complete loop. You can like trace it with your finger or like the back of your, like the eraser of your pencil or whatever, or you can actually draw it. So this is a loop. This series circuit has only one loop. That is actually the defining feature of a series circuit, that there's only one path for electrons to move. So for any complete loop in the circuit, the voltage across the battery must equal the voltage across the remainder of the loop. Now, there's a little bit that I want to go into here, but the short version is if I add the voltage through 5 and 6, it has to be equal to the total voltage. So voltage is all about energy. So if we tell the story of an electron, it starts in the battery. Inside the battery, there's a chemical reaction, and that increases the electric potential energy of the electrons. So the battery helps the electrons store energy because of the electric field. So the electrons have a lot of energy stored when they're in the battery. When they leave the battery, they have to do things, right? They have to like push their way through wires, and they have to push their way through resistors. So as they travel, they're losing energy. In our world of theoretical physics, wires don't take energy, but resistors definitely do, and light bulbs definitely do. They convert it. So the electric potential energy of the electrons stays constant until they get to the resistor. The resistor takes some of that away to make heat, and then the electron is left with a little bit less. Then it gets to this next resistor, and that resistor takes the remainder of the added energy from the battery. The electron returns to the battery with the same energy it had when it got to the battery the last time. So the battery is like a reset. When electrons get to the negative terminal, they have the least amount of potential energy that they're ever going to have. And when they get to the positive terminal, they have the most. So they get a bump in energy. We say that's VT. And then their energy is converted away from them in V5 and V6. So in a series circuit, you add the voltages. They add up to the total. Now, that doesn't mean that if you add another resistor, you get more voltage. What it actually means is if you add another resistor, the total voltage is divided between 3 resistors instead of just 2. So if I added like a third resistor over here and called it like Vx, I would have to then add it to this equation. And as you can see, I didn't actually change the total voltage. I just changed the number of resistors. So if you add another resistor, the original two get less because this new resistor is sharing some of that voltage. Okay. In a parallel circuit, things are a little bit different. Now, I don't have a great set of colors here tonight with me, but that's okay. There are 2 loops in this circuit. First loop goes through 7. And so that's kind of like a red, as a red ink. And then the second loop goes through 8. It's a very subtle difference, but it's a purple ink. You can see it's a little darker. So there's 2 loops, and so I'll try and draw this in colors. So in a truly parallel circuit, you will have exactly 1 load per loop. That is the defining feature of a parallel circuit. If it's not only 1 loop, and if it's not 1 load per loop, it is not series or parallel. It is a combination circuit, and so we'll cover those later. Okay, so I have to write an equation. The voltage across the battery must equal the voltage across the remainder of the circuit. So I can say, okay, total voltage is the voltage across the battery. For this red loop, there's only a single thing on that loop, and so the total voltage has to equal the voltage across 7. I have a second loop, same battery, but this time the loop involves 8. And so I can write 2 equations. The total voltage is equal to the voltage across 7, and the voltage across 8 is equal to the total voltage. And so I can, kind of summarize that and say in parallel, each load gets the total. It's not the same thing as saying like the voltage is the same everywhere. You can say the voltage is the same across every resistor, but it's not the same everywhere. So there's actually like no voltage in the wires, because wires, we say, don't use energy even though they do. So those are the rules. And I would like you to stick around for a little bit longer because I wanted to do derivation, because the last property we haven't talked about is resistance. And so I want to show you where resistance fits into all of this. The last lesson is on equivalent resistance. Equivalent resistance is what you get when you put multiple resistors together in a network. And so all the circuits you've seen, they're either series or parallel, and they are networks, in my case, of 2 resistors. Now you can have as many resistors as you want, but 2 is enough to like show you what's going on. So here's how this works. In series, I want to know, how do I calculate the total resistance? So I start with the loop rule. The loop rule says that the total voltage here is equal to the voltage across this one plus the voltage across this one. Okay. So that's like the first rule that I have. Now there's some other things that we haven't talked about in this lesson. The other one is voltage equals current times resistance. So Ohm's law applies everywhere. You can't violate Ohm's law. Even if the resistance of something changes, it still has to obey Ohm's law. The voltage has to equal current times resistance. So I can make a substitution. I can say that every voltage is going to be now I times R. So I can say, okay, well, instead of total voltage, I have total current times total resistance. Instead of V9, I have the current through 9 times the resistance of 9. And then for 10, I have the current through 10 times the resistance of 10. Alphabet soup at this point in time. Now, the other thing that I know is because of the junction rule that total current is equal to the current through 9, and it's equal to the current through 10. In other words, these currents are like terms. So I can divide this entire equation by the total current, and it will actually eliminate all of the current values. And so what I'm left with is this. The total resistance is the value of the one marked 9 plus the value of the one marked 10. So what does that mean? So my total resistance is what I get when I add the two resistances. So in a series circuit, I add for total resistance. And that hopefully makes sense. If I put more and more resistors in series, there's more things to oppose electric current, and so that's that. Cool. Last bit. What if I do the same thing with the parallel circuit? So I'll go through this one. The rule's a little weird at the end, but it's fine. We're going to start with the junction rule. The junction rule says the total current is what I get when I take the current that goes through 11 plus the current that goes through 12. So I just have to start with a relationship, and I start with the junction rule. Again, I have V equals IR, but because I have current here, I'm going to use I equals V over R. So I substitute, and I have now total voltage over total resistance equals V11 over R11 plus V12 over R12. The loop rule, so this looks really similar, right? Well, similar but different. I'm doing the same sorts of things. I start with a Kirchhoff rule, I substitute with Ohm's law, and then I do something else. The loop rule for parallel says the total voltage is equal to the voltage that each one of these receives, because each one of them is on their own loop. So again, I can take this entire equation and I can divide it by total voltage, and everything goes away. The equation I'm left with this time looks a little bizarre. It's flipped on its head. So the total resistance is now an inverse. So the reciprocal of the total resistance is equal to the sum of the reciprocals of all the individual resistances. That's a crazy equation. This is how parallel circuits work. And so to get the total resistance, you have to take the reciprocal of each resistor, add their reciprocals together, and then take the reciprocal of the result. And it has the effect of the more things you put in series, the lower the resistance is. So that's our one last long lesson of the unit, and so now you've had it. I am going to ask you to practice on the worksheet that the sub has given you. It should have the rules written up top so you can kind of organize them, and do what you can. When you kind of run out of steam or you finish, move on to working on your project. Thanks.